Okay, so the welcome back to the meeting, or the second week of lectures. So I'm going to just very quickly repeat some of the basic messages which we had last week, and then we're going to dive into this week's topic. So just quickly, the official website is the one which you get to by searching for FYS4480, and that's cloned with the PhD variant. And obviously we have to look at the 26 version of it. And if you go to the schedule here, you will typically find for every week so now we're just displaying this week, and then you will find the lecture material as both PDF and Jupyter notebooks. And these are roughly the topics. We are going to wrap up some of the calculations from last week, and we will most likely use one plus a little bit more of these lecture sets. And then we are moving into second quantization. This is what will keep us busy for basically the rest of the semester, that kind of formalism. So that was the basic website. You will find all the messages which we send with updates about the plans for the weeks and so on. You will find them here, but you will also receive an email. And I guess everybody has received the email here because everybody is registered. So on Canvas, you should then find the same announcement as well. So actually 3 sources: email, Canvas, and this one. And then you have the down here, you have the link to the teaching material. And this is roughly the layout of the GitHub site. And if you go to the doc folder, and sometimes actually this Edu-Roam has been pretty slow in the last days. I don't know if you noticed that. But the weekly material is the one which you find in here. And now we are week 35, and there you find the slides, which is this file here. And then you also have the Jupyter notebook, which we sometimes will run for demonstrations. But if we now go back to the material for this week, so let's just look at the plans for today. So let's take a look at that one. So the basic plan today is first to give you a quick reminder of what we did last week. And then hopefully towards the end of this lecture, we will begin with the second quantization. If not, this is something which we will look at tomorrow in more detail. So the reading the slides, I mean, I normally point to some specific chapters or sections of the textbook. And we also have the textbook of Szabo and Östlund when it comes to the calculation of expectations values without second quantization. And you can also play around with some of these Jupyter notebooks, which then contain some demonstrations, in particular of second quantization, which could be useful. So I'm going to go through first a quick reminder, say something about variational principles, expectation value with Slater determinants, and the problem with what we normally call first quantization, which is a kind of misnomer, as I said last time, why it is not the preferred notation. And this is a kind of motivation for second quantization. And then we are going tomorrow to look more into second quantization. So my hope is actually to get to this point today, but sometimes I'm a little bit slow with my handwriting and when I write down the notes on the whiteboard. So let's see how far we get. So if we don't reach this point today, we will start there tomorrow. So just a quick reminder. And what we did last week, we computed the quantum mechanical expectation values with what we call a Slater determinant. We did this by hand, and we just used all the degrees of freedom, spin and spatial degrees of freedoms, etc. And we did this for 2 particles. So we're going to rederive, actually we're going to rederive this for many particles. We did this for 2 particles last time. And what we saw for 2 particles is this is just a sum over what we call the occupied orbitals. And this expectation value here has a direct and an exchange term. And the exchange term comes from the fact that we are dealing with the Pauli principle, the way we parameterize an ansatz for the wave function in terms of a determinant. So I'm going to bring up these things again and again today because it takes some time to digest everything. And the thing is that this becomes a very meticulous calculation when you move beyond two particles. And this is one of the motivations, one of the many motivations for introducing the number representation or second quantization, that this becomes, how to say, not that practical when you're going to set up calculations for more than just two particles. So a quick reminder again about the single particle basis which we have chosen. So we are using and we are assuming that the single particle basis is a meaningful approximation. This is a very important approximation which is made, or assumption, because we assume now that we can build a many-body system starting with a single particle basis. This is an ansatz and an assumption about the system which is valid in case interactions are not very strong, or if a single particle picture makes a meaning. So single particle degrees of freedoms do not exist. There is nothing like a single particle energy. Sometimes the experimentalists may actually say that we are looking after single particle degrees of freedom. It's a many-body system we are looking at, and a single particle degree of freedom is something which you project out of the full many-body wave function. But this serves as a kind of approximation, and it's a simple way of building up a many-body ansatz. And we are going, since we are going mostly to deal with fermions, I didn't get any comments from anyone who wanted to look at bosons as well. So fermionic systems are often those which you encounter in condensed matter physics, in atomic physics, molecular physics, quantum chemistry, nuclear physics, etc., etc. And we are going to assume then that we can split the Hamiltonian into a part here, which just contains single particle operators. So these are operators which act on one particle at a time. And these operators are typically given often by the kinetic energy, which I'm labeled with a T here, and some kind of external potential, which confines the motion of the particles. So this could be the potential which is set up by the atomic nucleus in an atom, or it could be an artificial potential which you can make by setting up voltages in semiconductors. And these potentials could trap, let's say, an electron. These are just examples. And if you want to look at a purely academic example, many of you have encountered the harmonic oscillator. This is one of the classical potentials which is often used as a model for these kind of potentials, the external potentials. So you can think of you having a single particle which has its kinetic energy, and then it moves in a potential which can trap the particle. So this is an external potential which is mounted by the systems. If you're looking at nuclei, there is no external potential. What binds protons and neutrons is actually the strong force. And this is something you could parameterize in terms of an interaction between two particles. Now, the assumption then, which we made last week, is that this H0 is a problem which mimics essential physics of the system. Some of you may have taken a course in density functional theory or studying density functional theory. That's a typical mean field problem, where you then assume that you can extract a single particle solution to that problem, and that these eigenfunctions, these psi alphas, which you see here, they form an orthogonal and normalized eigenbasis, which we then can use as an ansatz for building a many-body state. And that was essentially what we did last time. What we're also going to do now is, since we don't want to carry with us too many labels, we are going to make a specific labeling here, which I'm coming back to. So I will, this is just for making the notation much more compact. And it's a notation which is widely used in quantum chemistry and also in nuclear physics. I'm coming back to what you see here a little bit later today. Then this is the part which we are going to look at, and I'm going to dive into my whiteboard now and just remind you of some of these things. And then we are going to calculate the expectation values of these Hamiltonians H0 and Hi when we have more than 2 particles. So last week, we looked at just the calculation for 2 electrons or 2 particles. And there we found an analytical expression in terms of integrals, which obviously needs to be defined. And then we are going to calculate the expectation value of the energy. So let's stop with the slides here and then move back to the whiteboard. So let me just bring up that one. So I wanted to remind you quickly a little bit about what we did last week. So the example which we looked at last week, we now just put it down here. So last week, we looked at 2 electrons or 2 particles. We had n is equal to 2. And then we made an ansatz that we had 2 states. So we had an H0, which now acts, and now I'm skipping the spatial dependence and other degrees of freedom. So we had this 1, instead of alpha, we had a phi 1 times x, and this gave us an epsilon 1 of phi 1 times x. And similarly, we had another state, phi 2 of x, which was equal to epsilon 2, and then we had phi 2 of x. Now, the model which we had made was a model which could be used to describe atomic helium. That's just one example, but it could also be 2 electrons which are trapped in a specific potential. So we don't need to link it with atomic helium, but atomic helium is a case which many of you have seen in different courses. So what we did then was to look at the atomic helium, but you don't need to look at that. You could just think of this as 2 particles. And in that case, we use these states where we have the 1s, and this is the atomic physics notation for the lowest lying states in the hydrogen model of Niels Bohr. So this is basically the Bohr model, which we have borrowed here. So S stands for sharp. And in that specific case, I'm going to write the quantum numbers when we are in 3 dimensions. So these quantum numbers would be 1, 0 for orbital momentum, and 0 for the projection of the orbital momentum. In this specific case, what we could do now is that we could actually place 2 electrons. One will spin up due to the Pauli principle, which says that the total wave function has to be antisymmetric. That has as a consequence, when you use a single particle basis, that one orbital, so we are going to call these boxes here for orbitals, because they are defined by specific quantum numbers, and then we are borrowing all this notation from Niels Bohr, which introduced this concept of orbitals. So that you can think of the electrons moving in orbitals around the atomic nucleus. And then each one of these is now assigned to a specific number. So that means that what we did then was simply to assume that this box here is a box we label as 1, and this box here is what we label as 2. Then, if you think of atomic helium or any of these atomic systems, if we want to use these hydrogen-like orbitals, so these states are actually solutions to a one-body problem, but we can use them as an ansatz in a 2-particle problem. That's essentially the kind of recipe which we will follow. So then we could continue, and then we have the next state in the Bohr model, which is a 2s state. And in that case, we can also have 2 slots because we have spin up and spin down. I'm just leaving this as vacant because there is no particle in there. And then we could continue like this, and we could have the 2p, etc., because the states 2s and 2p are degenerate in the hydrogen atom, but this degeneration is lifted when you go into a many-particle system due to the 2-body interaction. So in this particular case, what we would have is n equal to 2 here. So this is n, the number of nodes of the wave function plus 1. That's the way we label this. And then we have L equal to 0, and ml equal to 0. And then in the next stage, we have n equal 2, but we have orbital momentum equal to 1. And then we take the values between -1, 0, and 1 here. In this case, we have 6 possible slots where we can place the particles. So that means that if we now make a drawing here, there is a slot here, which we can now start labeling as. So the labeling here is just something we choose. You choose the ordering. And that means that we could now put a 5 here. And in this case, we have 6 slots. So 5, 6, 7, 8, 9, 10. And if we had 10 particles, this could be an ansatz when we fill all these for atomic neon. I hope this doesn't sound too trivial here. Just a reminder of what we discussed last week in order to set up the ansatz for the wave function for the atomic helium case or the 2-electron case. So you can replace this kind of quantum numbers. You could now, instead of doing that, you could do a one-dimensional harmonic oscillator. So HO is harmonic oscillator. In that case, your trapping potential looks like this. This is also a system which has an infinite amount of bound states. They're all bound to move in this harmonic oscillator trap, but they can leak out. There is a small probability that they can actually leak out of the potential, but that is almost negligible. So this would typically begin with n equal to 0. And in that case, since it's only one dimension, you don't have any other quantum numbers. The number of spatial degrees of freedom, which you have like here, that follows from the fact that you're in 3 dimensions, and then you have 3 quantum numbers. In 1 dimension, you have only 1. We would typically label this energy as something like an epsilon 0. Then we have the next state, and this would be n equal to 1. You can label this as epsilon 1, and this can go on. Now, in this case as well, you could now have one slot here with a particle with spin up, and one slot here with a particle with a spin down. And again, you would label this as 1, 2. But now in your case here, these states have to be, since you only have one spatial degree of freedom, one quantum number here, you can only have a spin up and spin down. So the kind of degeneracy you had from 3 dimensions with a 2p state here is not something which occurs in 1 dimension here. So that means that if you keep filling here, you would have a system where the system is just doubly degenerate at every level due to the spin degrees of freedom. So if you do the same labeling, this will be again 3, 4, 5, 6, etc. Now, one thing which we saw on the slides, which I want to bring back here, is this labeling, which I'm going to use for the rest of the semester, which gives a compact way to label these specific states. And this has to do with the fact that we are now making an ansatz for the ground state of the system. So this ansatz, which is also meaningful for atoms and this kind of systems here with the electrons trapped in harmonic oscillator cases, actually in condensed matter physics and semiconductor physics, these kind of potentials mimic the behavior of very important systems in semiconductor physics. Has anyone here heard about quantum dots? So quantum dots would be a typical example of something where you can approximate the trapping potential with a harmonic oscillator lookalike. So lookalike in the sense because the potential can probably look more like this. A harmonic oscillator has an infinite set of bound states. A real physical system has a limited number of bound states, and then these particles can escape from the system, and then you have a continuous particle spectrum, which is just given by kinetic energy plus some correction due to a trapping potential. But you see that the lower lying part of this potential is a harmonic oscillator lookalike. So it can be used to model this kind of systems. And that's why the harmonic oscillator is so useful as an approximation to model an Hamiltonian. Okay? So this is just a little bit back and forth about how we can relate the mathematics to real physical systems. So I'm going to introduce a notation now because we are going to use an approximation for the ground state, which is going to define something which is called the Fermi level. That means we fill states up to a certain level. So this is very schematic. But you can now think of, if you look at the atomic neon as another example, and you have this single particle basis, you could now start with 1s. You have the 2s orbitals. This degeneracy is lifted from the hydrogen atom. And then we would now make an ansatz here where we assume that the ground state is something which we now can approximate by filling in 10 electrons here. So 2p has a degeneracy of 6, 2s and 1s has a degeneracy of 2 each, and that means I can put in 10 electrons. So we would typically call this for a Fermi level. Actually, you can measure these quantities experimentally, or you can extract from experiments something which defines a Fermi sphere. If you look at this large system with many, many electrons in condensed matter physics. But this serves us as more as a way of setting up a limit for where we now assume that the ground state is, where this function here, where we can make a useful approximation to that function. And then, in principle, if we use these hydrogen-like orbitals, we have an infinity of states here. So in principle here, we put an infinity, but we are going to put a mark here. So somewhere here, we are going to put a bar, which I'm going to label with a D here. And that is the last single particle state which we will include in the effective Hilbert space. In some cases, you can make a very useful approximation mathematically, where you can actually define an effective Hilbert space. But in many, many cases, in most cases, this is defined in an ad hoc way. So you keep moving this limit here till the energy of the ground state doesn't change by a prescribed quantity. That's the standard ad hoc way, which is used in many body physics. When you put such a limit, that limits also the number of possibilities you have to you can distribute these particles in. Okay, does this make sense? So this is the basic kind of ordering which we will follow when we want to make an ansatz for the ground state. So this is the ansatz. But you see now that you can actually have particles up here, you can have move up here. So the total number of ways you can distribute, just let me remind you that, number of states you can make or configurations. So you will often hear me say configurations. And that's because the way you distribute the particles is a way to configure the system. And this is given if we now have n single particle states. So SP is a notation which I will use. SP stands for single particle. And then we have n, the uppercase letter n is the number of particles. Then these number of configurations which we have here is then given by the binomial coefficient, which you probably have seen many, many times. And that's given by n factorial, n minus n, and n factorial. And the assumption here is obviously that n is larger or equal than n. So if I make a space now for, let's say, atomic neon, where I only have 10 slots and 10 particles, then there's only one configuration. So if you look back now, let me just wait till everybody has been able to write down. Okay. If you look back here, suppose now that I leave out everything here, and I stop and I use this as my effective Hilbert space, then you see that in this particular case, there is only one state phi 0. So the only configuration you have then when you have 10 particles and 10 slots, it gives you just one possible configuration. And this number actually grows exponentially. And when we talk about the exponential growth of configurations and this wall of rising degrees of freedoms, then this is linked to the way you can make all these states here. Now we're going to use a more compact notation, because this case here is something which I have tailored to atomic neon or atomic helium. But when we want to be a little bit more general, I'm going to introduce a notation which I will use for the rest of the semester. So compact notation, and that was the one which I put up in the slides. So if we look now at this Fermi level, which I will often label just with F. So this is my Fermi level. This is an M. Then we are going to label states which are below this level with Greek letters. So this would be state 1, 2, 3, and it moves up all the way to N. If we have N particles, these are the states we can fill in. I'm going to label these with Roman letters I, J, K, L, etc. These are states below and up to the Fermi level. Then I have, since I have in principle an infinity of states, but I'm going to make a truncation up to D, so that is my truncation. I'm going to label these states with A, B, C, D, something. And since we mainly will just deal with two-body correlations, this lettering is actually sufficient. You may ask, because if we have many particles here, we should go to A, B, C, D, E, F, I, J, K, L. But we will mainly deal with two- and three-body interactions. And that means that these letters which we have here are normally sufficient to label these correlations and many-body expectation values which we'll get. So this will be states above F, and this will be states up to the Fermi level. Now, the other states which we have here, if I have a generic state, which I don't specify whether it's below or above, is something which I will just label with P, Q, R, S, etc. So this is the kind of labeling which we are going to use throughout the semester. Okay, any questions? Good. So what we are going to do next now is to, after we repeated a little bit, I just wanted quickly to remind you about the results which we got for the helium ansatz which we made. So in helium, with two particles, we now assume that the ground state, phi 0, is now given by two electrons here. So when we looked at helium, let's just put that one back again. For the ground state, so when we write this phi 0, you should keep in mind that this phi 0 is not an eigenstate of the Hamiltonian which is the Hamiltonian we want to solve the problem for. Oops. And we actually used the letter psi 0 here as a way to indicate the exact ground state. So we'll use psi to indicate that this is the exact solution, whereas phi 0, the way we are going to have it, is that phi 0 is actually the solution to this non-interacting case. And we wrote it as an epsilon 0 multiplied with phi 0. So the ansatz we made then, phi 0, with x1, x2, was that this was given by a Slater determinant, 1 over 2 squared, and then we had a phi 1 of x1, phi 2 of x2 minus phi 1 of x2 and phi 2 of x1. Like that. And this is something which we could write out as a determinant. Two like this one, and then we have phi 1 x1 and phi 2 of x1. So columns stand for the given particles and row stands for the specific quantum numbers or the slots where we are filling in particles. And when we calculated the expectation value of the energy, yeah. Say it again. Yeah. So in this, in the previous case, this is the way I would typically distinguish between occupied and non-occupied by the letters I, J, K, L. But now I'm going back to the case which we had last time, where we simply use these quantum numbers 1, 2. But in principle, if you go back to this case which we have here, you see also that you would have a numbering 1, 2 up to n here.
But so you assume that under the Fermi level,
yeah,
they are occupied?
Yeah,
okay.
yeah. So for this case with the helium atom, then we would then say that the Fermi level, which we didn't draw here, you would put the Fermi level here. So 1 and 2 would be the states you assume describe well the ground state. So this was what we did last time, and then we calculated the expectation value with that quantity. So if I take phi 0, and this is now the kind of approach which we are going to extend to more than 2 particles. So what we found then is that this is given by epsilon 1 plus epsilon 2 plus these integrals, which we wrote as 1, 2 of V 1, 2 minus 1, 2 of V of 2, 1. Let me just remind you what this is. So this is an integral over dx1 and dx2 here. And I have the integrals of phi 1, x1, phi 2 of x2 multiplied with the interaction x1, x2, and then multiplied with phi 1, x1, and phi 2, x2. So this more compact notation is something which actually is given by an integral. And the same with this one, except that then, in this specific case, we would have to interchange x1 and x2. This is called the first term is called the direct term, and the second term is normally called the exchange term. Now, the epsilon ones, these guys which you see here, they're actually given by an integral. So you will often see them in a compact way, like 2h0, 2, which again means that we have an integral over d of x by 2. And now I'm a little bit lazy here, so I may sometimes skip the x's. So and phi 2 of x here. And since the phi's are, the psi's are actually are eigenstates of H0, then they just become equal to a constant here, which is epsilon 1, epsilon 2, etc. Okay, so this was roughly what we did last time. So what we're going to do today is to use this and move on to n particles. And when we move on to n particles, you will see that the way we do this with this kind of approach becomes not too practical, quite wieldy. And then we are going to introduce second quantization, which will actually allow us to simplify the calculation of these many-body expectation values. So now we're going to move to n larger than 2. And we are still interested in then making an ansatz for the ground state. We have a phi 0. It doesn't need to be phi 0. You can actually, and you will get exercises next week where we are going to change the bra and the ket side. So the bra and the ket side can differ by 1, 2, 3, or more single particle states. And then the question is, how can we calculate these in an efficient way? So you're not limited to phi 0. Keep that in mind, because this is a course which, although we focus a lot on the ground state of the system, like the ground state for atomic neon, we have a formalism which can also be used to calculate excited states. So an excited state could be us looking at an excitation where these two s electrons are moved up to 3s state. That would be an example of what we will call an excited state. The thing which is nice with this single particle picture is that it allows useful physical interpretations of the results. And it gives us, obviously, a handy calculational scheme. That's important to keep in mind because we are making an ansatz where, so let's first set up this one. The ansatz which we have for psi 0 is this phi 0. This is not the exact state. That's an ansatz, which is based a lot on our intuition about the physical system. And the ansatz is now given by this Slater determinant, where I write x1, x2, up to xn, which is then given by 1 over n factorial, which takes into account all the possible permutations of x1. I have a phi 2 of x1, and this goes all the way down to n. So we are filling up all the states up to the Fermi level. So if this is atomic neon, n is equal to 10. Okay. Now, this is a Slater determinant, as we call it. And it's a way to bake in our ansatz, the anti-symmetry. So you know that the Pauli principle says that the total wave function should be anti-symmetric. So the other parts of the wave function here, because this is not the exact solution, it's an ansatz. It's the same ansatz which is used in mean field theories like Hartree-Fock theory. I guess some of you may have heard of that. And also density functional theory, which are ansatzes based on a single particle picture. But then you could obviously, the exact wave function, if somebody gave it to you, it could have components which included parts of this. So if somebody gives you the exact solution, you can obviously calculate the overlap between the exact solution and a Slater determinant, which is your ansatz, an approximation. And if you then make the comparison, you can actually then say how good is a single particle approximation. So when we talk about this Slater determinant, it's called a single particle approximation for a many-body state. Because we build a many-body state using single particle states. But this is not the exact solution. Okay? So that means that the other parts of the wave function, if this is the anti-symmetric part, they have to be symmetric. Okay? Or if you have two more components, they could both be anti-symmetric, because anti-symmetric times anti-symmetric becomes symmetric. But then you need something which keeps the anti-symmetry. That makes sense? So, yeah.
Like the determinant can like geometrically be thought of as like the degree of stretch that it provides, right? Or the degree of stretch that a linear transformation.
Yes, exactly.
So,
the way you do this is because you have an anti-symmetry which you want to respect. So the way we have baked in Pauli's principle that the total wave function for a system of spin half objects should be anti-symmetric. And till date now, there is no experimental deviation from that. So we believe that a system like, let's say, atomic neon, atomic beryllium, etc., is a fermionic system where the total wave function is anti-symmetric. So what we are doing now is simply to make a theoretical ansatz as a starting point for our calculations. But if I go back to what you said, this basis here, which you have defined, the single particle basis is orthogonal. That means also that you can make a basis of such Slater determinants, which is also orthogonal. So at the end, when we come to FCI theory, we are going to expand any of these states in terms of a set of coefficients which in principle run to infinity, but we have to truncate, where we now have these overlaps between the state 0 and j, and a total basis of Slater determinants. So this can be then represented by a unitary transformation of your original basis. So this phi j's here would then correspond, if you go back to this figure we made for atomic neon, then that could be, suppose you stop with a 3D here, then you can have a given number of Slater determinants, which you can make up when you distribute 10 particles. That would be the basis of Slater determinants, which you would include in this expansion here. And then the exact solution would be a unitary transformation of this basis into the exact solution. Did that help more, or did that answer what you were thinking of? Was that what you were thinking of, if I understood you correctly?
I don't think I know the physics to understand.
Okay. We could discuss that during the break, actually. But the whole thing is that, and this is the basic idea of what we are going, the method we are going to meet, which is called full configuration interaction theory, where we then can set up a finite basis of such determinants based on a single particle basis, which we have chosen and which we think is meaningful. And then we can set up a problem which leads to a diagonalization problem in this basis. And when you diagonalize, the eigenvectors are actually these coefficients. And this method is called full configuration interaction theory, or just configuration interaction theory, or just CI. Because you're setting up all the possible configurations here based on that single particle basis. So keep in mind that, as I said also in the beginning, this course is about us finding approximations to a physical system. We don't know this solution. So then we have to bake in the physics knowledge which we have and build up a basis which is with something we think is meaningful, like building up for atoms using hydrogen-like orbitals, which we hope is meaningful. And actually all calculations show that you get a pretty good agreement with experiment. So if you look at that case with helium-2 with just the singlet or this 1s states, you get something like roughly 85% of the correct energy, which is not bad. It's a good, that shows you that that is a good approximation. And then the rest are correlations which you cannot bake in by a simple single particle picture. As I said, I mean, we have also cases which we are going to discuss here where you have Hamiltonians which give you exact solutions for many body systems. This quantum dot case with a harmonic oscillator is a case where you can solve analytically the two-particle problem. And then you can compare that exact solution with something which is built up by a Slater determinant only with harmonic oscillator-like orbits. And when you take the overlap, you can then see how far away that assumption is with respect to the exact solution. So there are many body systems with simplified two-particle interactions which can give us analytical solutions. And these are just invaluable because then we can test our theories against that. Okay. So let's just wrap up a little bit here. If you look at this Slater determinant, has any one of you met the Leibniz representation of a determinant? Does that ring a bell back from mathematics courses? So there is a compact way which we are going to use after the break. And let's just stop here when we've done that. So Leibniz rep for a determinant, representation for a determinant. So let's set up a matrix A, and this matrix is then given by some A1, A12 up to A1n. We are assuming this is a square matrix. We are not assuming that it's a symmetric matrix, but we don't need to deal with that now, but we're assuming it's a square matrix, N1, and then we have all the way up to Nn. So in Leibniz representation, this determinant of A is given by a sum which where this P is the sum over all the permutations which you can make. So when I think of a permutation here, I'm just thinking of permuting column 1 and column 2. So that's a permutation. But I can also permute column 1, 2, 2 and 3, etc., etc. So all the possible permutations you can make are then spanned by this variable P. So when I say N here, this is, I'm just writing this, these are all the possible permutations I can make. And this is given by the sign, which is of P, and multiplied. And then I have from I equal 1 up to N. And then I have the element AI, and then I permute columns. So P on I is just a permutation of the column. So quickly, before we take a break, let me just show you what this looks like for a 2x2 determinant, because then you will see immediately what this P is doing for us. So sine P is just -1 to the power of P. This is the kind of expression which we will use now in the calculation of the expectation values of the energy. So just take an example with a 2x2 determinant, A1, A2, A12, sorry, A21, A22. We know that this one is equal to A11, A22. So these are the diagonal elements. But then I have minus A12 of A21. So what have we done here? You see now that what I've done is to interchange columns 1 and 2. And this is what we have if you look at the P in the previous case, this kind of strange notation which I put up, this here. This is us interchanging. That's the, we have the 0 permutation, and then we have the first permutation of the columns. Okay? So Leibniz representation is just a more compact way of setting this up, and you see you have the minus sign. Yeah?
To go backward.
This one?
E there, it isn't the actual permutation, it's like the index of the...
Yeah, that's the index, yeah. So it sums over all possible permutations. So if you have if you look at the, so after the break, we are going to look at a 3x3 determinant. So let me just set it up here, because this is where we'll start after the break. And when you write it out, what you will have is A11. And in the first case, you have an A22 and A33. And then you have minus A11, and then A23, A32. And then you have 4 more, which we will look at after the break. So this will be the ordering 1, 2, 3. Whereas this one is now a change where you have a swapped 3 and 2. So I would just label that if you think of an ordering here, right? So this ordering 1, 2, 3 is what you would call the basic ordering. So last one thing before we take a break, because this one is the way we are going to order the single particle states when we calculate the expectation values. And this ordering is going to follow very much the physics of the single particle states. So let me just say why before we move on here. So if you look at like this case here, you see now that I could now say that these 2 states here, these are states 1 and 2. So that would be phi 1 and phi 2. and that translates into the matrix elements in a determinant of A11 and A22. And then I have the next ones, which will be A33, A44, etc. And so I can make a hierarchy of this matrix where the diagonal matrix elements correspond to these single particle states which I have here, which are ordered in an ascending way according to these single particle energies. So when I'm setting up the Slater determinant, and you saw that for the two particle case here, the diagonal here is then just given by the product of these two lowest lying states. And that's why we like to, when we rewrite the Slater determinant, we are going to rewrite in terms of a function which is just given by the product of the single particle states, like that. And the rest are just the changes you can make between different columns. And for a 3x3 determinant, you have 3 factorial possible types of permutations. And you see that immediately here, right? When you write it out, you're going to get 6 terms. Too trivial? Or I think it's good to remind ourselves about these things, because there's a lot of nomenclature in this course, and there's a lot of jargon which we use, which is actually linked to this mathematics which you see here. We'll take a break. I went a little bit over time. It was a little bit deliberate. So we begin at 11:20, if that's okay. Just, we need 15 minutes, right? Okay, let's take a break. Okay, so let's continue here. So what we discussed before the break was this, or introduced, was this compact notation given by Leibniz. You may have seen that in courses in linear algebra, or alternatively, you can just think of this as many of the many hidden gems in linear algebra. State them, but I will not prove them. But the way to look at this is simply by setting up a 2x2 of, then you will easily see the type of permutation. So if you are dealing with a 3x3 determinant, you would then have in total something like a 3 factorial. So that means 6 possible permutations. And the first 2 ones are obviously those which you get when you use the traditional formula for the determinant, where you simply take this subdeterminant and multiply with that coefficient. Then the next one would be A12, and then you have these 2 and these 2. So we can just keep adding here. So I'm just going to put parentheses here to indicate that this is the type of changes or permutations which we get, right? So this will be 3, 2, and the other one is unchanged, the first one. And then we know that the next one will just be an A12, and then we would have an A21 multiplied with an A33 minus an A31 multiplied with an A23. And this goes on. So, and you can easily see here that in this particular case, in the next one, you've actually swapped the 2 and 1. So this would be something which you could label as 2, 1, 3. And this just continues. And in total, you have 6 possible permutations. Yeah. But you just decide, I mean, which one you use, right? Because in this specific case, I've taken the columns. So I did A11, A12, A13, but there's nothing which hinders you by taking these factors and then calculate it. So you just decide. And I like to use columns here because the way I'm organizing these Slater determinants is that I have the particles in the columns. So this is particle 1, particle 2, up to particle n here. And then I'm just interchanging the position of 2 particles. So this is just one way of organizing it. And that's why I've been using columns. Alternatively, you could do the same thing with rows. Okay? So this kind of compact notation is a little bit interesting for us because we can set up a more compact way of calculating these expectation values. And if you go into most textbooks in quantum chemistry or many-body physics, where like Sabo and Oslund, in their first 2 chapters, you will see this operator which is being introduced, which is called an anti-symmetrization operator. And this is an A, which is now given by 1 over n factorial. And then it has the same sum over all the possible permutations which we can make, minus 1 to the power of p. And now what I'm going to do is actually to introduce a kind of notation which I'm not happy with, simply because if you have many such objects here, I want to avoid to write it like this. So I'm just going to indicate this one with an operator. And I'm just going to call this, since I'm doing all these permutations, I'm going to write this as an operator P. Okay? So I'm not happy with the notation because I also been using that as a projection operator. But in this case, this is something which will just interchange 2 columns or more columns. Okay? So it represents the possible permutations which we can make. The thing which I'm just going to state here without proving it, except for the trivial case with n equal to 2, is that this is an idempotent operator, which means that if I square it, it's equal to itself. And this is going to be useful when we are going to calculate expectation values. There's also another thing which I'm not going to prove, but you can it's actually not that difficult to prove it, that this operator, if I take the complex conjugate, it's equal to itself, the emission conjugate. And then if you look at n equal to 2 here, if I now calculate this A, and I put a 2 here to indicate that this is for 2 particles, then like the helium case, this is going to be equal to 1/2. 1 minus this operator, which I indicate with a 2 here, to indicate that I can have 0 permutations of the columns and 1 permutation, like we had for the helium atom, which we looked at. So it's not this P is not the projection operator which I introduced earlier. So when I square it, this is going to be equal to 1 divided by 4. I'm going to have 1 minus, and then I'm going to have a P2 times 2. I'm just multiplying out the terms, plus this P2 squared. Now, when I make a permutation, so this guy here, if you think back to the Slater determinant, we had A11, A22, and then I had A minus A12, A21, okay? So this one here represents this permutation which we looked at between columns 2 and 1, okay? So I'm just writing it out as we wrote out the Slater determinant. So I know that if I do this twice, then I'm back to the same. So this one is actually just equal to +1. Because if I interchange first column 2 and 1, and then I do it again, then I'm back to where I was. Does that make sense? So for the 2-particle case, this is pretty trivial. It's not so difficult to show it for free. I haven't tried to show it in a general case. So this is an example where I will just state a result which you will find in the literature. But I guess this is not so difficult to prove it. I haven't tried it. Maybe I should do that. If I now write this out, this is simply equal to 1/2, and then it's 1 minus this P2. So P2 is the one where I interchange columns 2 and 1 here. As I said, it's a notation which I'm not happy with, but I hope you can live with it. The important thing for us is also, and this is not so difficult to prove actually, is that this operator commutes with a full Hamiltonian. it commutes with H0, and it commutes also with, and this is also something I'm stating without proofs. And this is these are features which are going to be interesting for us when we're going to calculate specific expectation values. Now, one thing now is that we can use this operator to write the Slater determinant in a very compact way. So the Slater determinant which we had previously, this operator here, which if we now write it out in full glory, this is something which we would have as a phi1, x1, phi2, x1, etc., all the way down. So this is going to be one of the last times when I write the full Slater determinant. So you see that this Slater determinant formalism here is begging for something which is more compact. And that is what second quantization is going to give us. Because it's not fun to write this again and again. We can actually write this, and it's not so difficult to see it from the definition of 1 over n, the sum over p, and the sum over all the possible permutations which we have. Not that way, because that was the one I set up earlier. If I take that operator, this is going to be n factorial multiplied with this operator, the anti-symmetrization operator. And then I have a function which I'm going to define now. 1, 2, x1, x2 up to xn. And this function goes back to the ordering which we have chosen for the determinant. So this function, which you see here, is called the Hartree function. So I'm going to bring it in here, the Hartree function. And this function is just the product state of all the single particle states. So this would be phi1 times x1, phi2 of x2, up to phi n of xn. Now, if you think of the determinant by itself, then this would correspond to the matrix element A11. This would be the matrix element A22. This is a product of the diagonal matrix elements. If you just think of a determinant. Now, in our case, this labeling which we have is something which can often follow the natural order we have chosen for the single particle states. So psi1 here could be the lowest lying single particle state, psi2 the next one, etc., etc. You can obviously organize these states in a specific way, but when you have chosen an order, we normally call this the ground organization or the basic organization of the state. And then you can express all other Slater determinants or all other parts of the determinant in terms of permutations of this ground ordering. Because you know that for the 2 by 2 determinant, the only thing you had then was a minus A12, A21. If you have 3, you get 5 more in addition to the basic ordering. So this kind of ordering is something which is often intuitively dictated by the physical system you are approximating with a single particle basis. So it means that if the energy of these single particle states up to the Fermi level have a specific ordering in terms of energies, then it follows that you could say state 1 is the one with the lowest single particle energy, state 2 with the next lowest, etc., etc. So the basic ordering which you've chosen allows you now to express all these other components in a Slater determinant in terms of permutations of that. Okay? So why is this interesting? If we now look at this basic ordering here, when we now write an expectation value, suppose now that we want to look at the expectation value of phi 0 with the non-interacting part of the Hamiltonian. So let's just write it out in terms of this new type of notation. And then you will see immediately then that if we use these commutation relations and the property that a squared is equal to a, then we can simplify the expectation values. Still, it's going to be clumsy, and you will see that second quantization simplifies considerably the way we calculate these expectation values. At the end, what we want to is to have a simple recipe, which is intuitive and which allows us to calculate efficiently, both on a computer and in the traditional human way by paper and pencil, things in a very efficient way. Okay, so let's just write it out now and see what we get. So if I write out this term with this new notation, I can then write it out as n factorial. And then I'm going to explain what this d tau is. I'm using a little bit more compact notation here. And then I have the complex conjugate of this Hartree function. I have the Hermitian conjugate of the operator. I multiply this with H0, and then I have the operator again, A, and this is multiplied with this Hartree state. Now this d tau is just a compact notation for dx1, dx2, up to dxn. Remember now that x of I is something which can encompass both the spatial degrees of freedom and the spin degrees of freedom. So we've just been using x now as a generic variable for each particle here. But then when we look at the specific case, we have to go down and say whether this is a two-dimensional quantum dot, whether this is atomic neon, or whatever kind of physical system you're looking at. So what I can do next now is to use the commutation relations. And I know that since H0 commutes with A, and then if I just interchange A with H0, then I get A squared here, and A squared is equal to A. So this quantity here, if we just put this away, is going to be equal to n factorial. And then I have an integral over d tau, and then I have this Hartree product, which is just a product of the single particle wave functions. Keep in mind that the Hartree function does not respect antisymmetry. It's just the product state. It also doesn't respect the symmetry of the state. So it's just a product state of single particle wave functions. And then this is multiplied now with H0, and then I have A, and multiplied with phi of H. So the only thing I did now was to replace A with H0 with H0 times A. And then I know that A squared is equal to A. And I should remember to put hats on operators here, because that's something I easily forget to do. So if you see me forgetting, I mean, these quantities are operators. So I should keep in mind that I should put hats on them, but it's easy to forget. Now, if I now look at this one, I can now start plugging in the expression for this operator A. So if I do that, there is a 1 over n here when I plug in that operator. So what I'm getting is a simplified expression, which is equal to this integral over d tau, phi of h, and then I have h0. And now I have the sum of all these permutations. Minus 1 of p. And I'm bringing back this very unfortunate notation, which I'm not pleased with, like that. Okay. So if I now do 0 permutations, because this is just a sum of all possible ways I can interchange particles 1 with 2, 3, 4, 5, and 6, etc. So the first case I'm going to look at is 0 permutations. Let's just write it out here, because if I do 0 permutations, what I'm going to get then is the following. So I will have a dx1, an integral over dx2, etc., or to dxn. And then I have the Hartree function, which in this case is simply psi1 of x1 complex conjugate up to psi2, psi n of xn complex conjugate. This is then multiplied with the h0, x1 plus h0, x2 here, plus h0, x of n. So each one of these acts only on a given particle. And then with 0 permutations, what I have is just the Hartree function itself. This should not be complex conjugate, obviously. x1, phi2, x2, up to phi n, xn. Like that. This is the 0 permutation case. And in that particular case, what we know now, this is roughly just a generalization of the case we had last week for 2 electrons or 2 particles. So each one of these, this one, obviously has to connect with this one and that one, because these act on x1 and that one. Then all the other ones in this first element here, all the other ones will just be integrals with dx2, and then there will be a phi2 with phi2 here and x2. And since these are orthogonal basis functions, they all give just 1 for the integrals. So what this term is actually going to look like is just a sum over all these integrals, where we now can have a sum from 1 to n of the integrals, which we have labeled typically before as this, which again, since these i's are eigenstates of H0, this is simply a sum over all the single particle energies. So were these integrals, just to remind you, are just a d of x over phi of I of x and phi of I of x. And we have obviously assumed now that these basis functions which we have chosen are eigenfunctions of these H0 operators, the single particle operators, which contain just an external trapping potential eventually, or they could just contain kinetic energy only. So this is equal to eps of I of phi I of x. So this is the kind of assumption which we made. And the other assumption is obviously that this is an orthonormal basis, which means that if I calculate this quantity here, I get a Kronecker delta. Now we can start looking at all the possible permutations. So one possible permutation is to interchange 1 and 2. Another one is 1 and 3, 1 and 4, 1 and 5, up to 1 and n. And then we can do 2 and 3, 2 and 4, etc. These are all the possible permutations which we can make here, right? Yeah. A generalized S?
X.
Yeah, this is just it could be any one of these xi's which we have in here, right? So instead of writing x1, I'm now just putting just x here. I could have put dxi here, but this is just it's just an integration variable. The thing which matters is actually this state here. That's the one which is important, because that gives a specific eigenstate. The rest here are just dummy variables, and you can call them whatever you want. So let's now take the case of just one permutation, because that case will tell you, you can see that immediately, that all other non-zero permutation cases are going to give us 0. And you will see quickly why. So 1 permutations. And we can just pick an example, and that example is enough to see that all the other permutations, whether just interchange 2 and 3, or interchange 2 and 3, 5 and 6, etc., will give us zeros. So one permutations. And let's now just change 1 and 2, okay? Because you will see that quickly now that this is going to give us 0. And this will apply to all other permutations. And I should say, and applies to all other. With second quantization, this is going to be much easier to see. But let's now write this integral again, but with just interchanging 1 and 2. So what you get then is a dx1 and dx2, etc. And then this follows all the way up to dx of n. And then it's multiplied with by 1. And now I'm not doing the permutation here because the bra side is unchanged. Up to phi n of xn. And this is multiplied with the sum of h0 of x1 plus h0 of x2 h0 of xn multiplied with, and now I'm making the change here. So this is x1 and x2 being interchanged. And x1 here. And the rest is unchanged. So the next one is 3 with x3, etc. So this is unchanged. Only that one. Okay, this is one of the possibilities. And if you have a 3 by 3 determinant, then you have 6 such possibilities. So if you're a little bit in doubt, it can be okay, because still with a 3 by 3 determinant, you will only get 6 possibilities here. So it's something which is doable by paper and pencil. It's not so fun, but you can quickly see now by just this example here that all the other ones have to be 0. If you look at this now, the only thing which gets affected is this one with that one acting on this one. So this will be a specific contribution where you will have dx1 with phi 1, x1, h0, if we now are looking at x1 here, multiplied with phi 2 of x1. This obviously has another integral, which goes like dx2, and then I have a phi 2 of x2 and phi 1 of x2. And then all the other ones for this specific case, where we now look at only the x1 contribution, that means this guy, and then you have similar sums here. Then this one will have x3 with phi 3, x3, phi 3, x3, etc. in the last one. And now you see that this one has to be 0, because if you look at this term, let's just single it out. If you look at this specific term here, this one is 0, because you have a h0 acting on phi 2, which gives phi 2 times a constant, and these two states are orthogonal. And you see here as well that this is also orthogonal. So that one is also equal to 0. So any other permutation than the ground permutation, 0 permutation, gives 0 results. So that means that the expectation value of this quantity here is simply equal to the sum over the single particle states, the single particle energies. And that means also for us that this H0, which we had, Hamiltonian for the many-body H0, acting on phi 0, is given by an epsilon 0 times a phi 0. So this phi 0, these slated determinants we've chosen, are eigenstates of H0. And this epsilon 0, for this specific case, the choice we have made, is simply the sum over all the single particle states. So I should make this a little bit smaller to indicate that there's an upper case epsilon and a lower case epsilon, which are the single particle states. So this means in general, if I make any other Slater determinant, that these Slater determinants are actually the eigenstates of this operator H0. So that's a very important result, which we will come back to later. Now we can repeat the same exercise with the interacting piece. And in that, for the interacting piece, what you will see then is that we are just going to get two terms only. And let's see that. So let's now look at phi 0 with the interacting piece. And we are going to make the assumption now that this H of I is just a two-body potential where we sum over all the particle degrees of freedom of xi, xj. And this potential is now a potential which depends only on the relative distance. This is typical for most two-particle potential. If you think of the Coulomb potential between two electrons or two protons, if you think of the gravitational force, there are forces which are typically physical objects, physical quantities which depend only on the distance between two objects, the relative distance. You can have more complicated forces, obviously, but this is an assumption which we will make in the calculations here, and that's going to help us a lot in setting up the final results as well. So let's now reuse everything we did previously. So it means that when we use this commutation relation and the properties of this anti-symmetrization operator, we can actually rewrite this one in the same way as we did with H0. So this is going to be equal to phi 0. Let me rewrite it in terms of integrals. So we're going to have an n factorial, and then we have the integrals, d tau, and then we have the Hartree state, and then we have h of I instead of h0, and then we have a, the operator, multiplied with the Hartree state. And when I plug things in here, this is going to be given by the integral over the spatial degrees of freedom and spin. And then I have my operator. I should put hats again on things. And now I have the sum over all the possible permutations I can make of P acting on this phi of H. So I have the same basic calculation line, and then I just get the same type of expression, except that I interchange the operator. Now, the problem now is that my operator is not a one-body operator, but it's a two-body operator. So I have to be a little bit more careful. But again, I would start with 0 permutations. So that's the simplest case. And let's see what we get then. In that specific case, if we now write everything out, what I would have, so I'm going to have a sum over I'm going to write out the products here of the integrals of dxn multiplied with phi 1 x1. So the Hartree state, the nice thing now is that we don't need to look at the anti-symmetry of this state, because last week when we did the calculation for the 2-electron case, we wrote in the explicit Slater determinant. Then this is multiplied with a sum over I less than j over these interaction elements. And this is again multiplied with, so with 0 permutations, what I have is phi 1 times x1, phi 2 x2, etc. Phi n xn. And now you see what we are going to get are integrals where when we now put in the labels here, x1, x2, etc. So this is just going to be given by a set of integrals, which is going to be given like this. So we are going to have a dxi, dxj, and then I have my phi I, xi, phi j of xj, multiplied with vxi, xj, and this is then multiplied again with phi 1, x1, and psi 2 of x2. No, sorry, I, and j here, like that. It should be pretty trivial to see that this is the case. And this again is what we labeled in a more compact way as an I less than j. And we wrote it in a more compact way in terms of the symbol with bracket notation here. And this is called the direct term, because we take just the direct product of the single particle wave functions. Okay, that makes sense? Then what I can do now is to interchange just one set of columns. So keep in mind that when we talk about interchanging these columns, we are not just doing 2 columns at a time, but if we have like 4 particles, we can interchange 1 and 2, and 3 and 4. Or we can just look at one permutation. When I say one permutation only, it's just taking 1, 2, or 3, 2, 4, 5, etc. So the one permutation case, so let's take a look at that again. So let's take one permutation. And let's now interchange x1 and x2, just as an example. Okay. So that is going to give us, when we now look at the specific contribution to the force, which we have there, so we have to be a little bit careful now, because we will have, if we now look at the terms, so we have dx1, dx2, up to dxn, and then it's multiplied with, so I'm sorry for being this kind of pedantic here, but I think it's useful to see it once and see how clumsy this formalism is, because then you will see the benefits of second quantization. Multiplied with phi n of xn. So there is going to be a term here where we take the interaction with x1 and x2, okay? And this is again multiplied with phi 1, x1, but now we have interchanged the x1 and x2, like that. The remainder here is just a product of a dx3 with phi 3, x3, phi 3, x3, all the way up to dxn, phi n, and I'm getting a little bit lazy here and I skip the x dependence. But then we have other terms. So this potential here has also terms where we have x1 and x2, right? x1 and x3. So there is a new term. And let's just write that one out. And I'm going to put the integrals like this, but there will be one where we now have x1 and x3. Plus more terms where we have v, x1, x4, etc. Because the sum here over the potential terms run over all i's less than j. So what I did now is to interchange x1 and x2, but I have to take into account all the other guys. Now, when you look at this one, there's going to be a term here which is going to give us 0. And you will see that immediately, because now in here, there will be an integral over dx2, which is not affected by the potential, but where you have phi 2 x2, but now multiplied with phi 1 with x2. That makes sense? And then you have all the rest. Similarly, when you look at x4 here, you will also have this same term. And you see that this is going to give us 0. So the only term which is going to survive is the one which now involves x1 and x2. And all these other integrals which you see here, they will just give us 1 or zeros. So with x1, x2, the only thing which survives is actually this term here. So this is going to be given by the integral dx1, dx2, and then phi 1, x1, phi 2, x2 here. And this is multiplied with x1, x2, and then phi 1, x2, and phi 2, x1. And this is something which we write in a compact way as 1, 2 of v of 2, 1. And this comes with a minus sign. It comes with a minus sign because we have to take into account the permutation. So keep that, minus 1, which we just left out here. So that means that this one should be minus and minus. All the other ones disappear. Now, this was one permutation. And now you see quickly that if I do x1 with x3, that will give me immediately minus, and then there would be a 1, 3, v, 3, 1, etc. This is one permutation only. So that means I take 2 columns and just interchange them. But the sum of all possible changes you can make is just not the case where you just interchange 2 columns, but you can interchange 4 columns, etc., etc. So it's all the possible permutations which you can make. And you see now that if I do more than one permutation, then I will have inevitably integrals of this type, which will give rise to 0. So the only terms which survive are those with one permutation. That means 2 variables which are being interchanged, and 0 permutation. So that means that the final expectation value, and this is where we stop today. I was hoping to reach a second quantization, but I was a little bit too slow here. This is just going to be the sum over I less than j of all these integrals of ij, v, ij, the direct term, minus this exchange term. So this is a kind of correlation in the sense that we bring in correlations due to the Pauli principle. This is not the exact energy, but it is often in atomic physics and for weakly interacting systems, a pretty good approximation to the energy. And when we deal with Hartree-Fock theory or density functional theory, this is actually going to be the same expression we will see, except that the single particle states are changed. But mathematically, when you have a Slater determinant and calculate the expectation value, this is what you will get. But this is not the exact function. So this course actually deals about how can we improve these results. It sounds like a boring exercise, but actually all of many-body physics is bringing in better approximations to the calculation of the states of a given physical system. Okay, should we stop here? And then tomorrow we begin with second quantization. And you will see that all these calculations are simplified. But not in the first round. It's only when we have introduced Wick's theorem that this can be simplified. Okay, take a break.